Hello everyone. In this video, we will discuss what the Fast Fourier Transform or FFT is and the algorithm needed to implement it in hardware. Also, keep in mind that this video is part of a larger series where we show how to run an FFT on an FPGA in two different ways. In the first approach, we will build a large Verilog design that directly implements the FFT algorithm. In the second approach, we will use a microblaze processor together with FFT IP to automate the process. But before we can do any of those things, we first need to explain the hardware level algorithm, which is what this video will cover. Alright, so let's get started. When we have a voltage signal that varies as a function of time, we always want an equation for it. The reason is because once we have an equation for a voltage source, we can then use that equation to do very precise signal processing operations on it. The equation below shows a hypothetical expression for voltage as a function of time. The unfortunate reality of signal processing is that a measured real-world signal is not handed to us as a neat equation. It is only observed through discrete samples. No matter how many samples we collect, the data by itself does not directly reveal the exact mathematical equations of the original signal. This creates a fundamental problem. Without a workable mathematical representation, meaningful signal analysis and processing becomes very difficult. So this is exactly where the FFT comes in. When sampling an external voltage, the process works in two steps. First, an analog to digital converter, or ADC, measures the signal at evenly spaced points in time. After collecting enough samples, we end up with a vector of numbers, vector S. This vector contains all of the samples taken by the analog to digital converter. Then, to recover an approximate mathematical expression for VFT, we apply the Fast Fourier Transform to that vector S. The FFT moves us from a list of sampled values to a frequency domain representation, which we can use to approximate VFT as a sum of sines and cosines. It's worth noting that this result is only an approximation, but in practice it's a very useful one. Now let's talk about how the FFT algorithm works. The FFT algorithm is just a mathematical operation that takes in vector S and outputs a vector K. Vector S is simply going to be a vector of real numbers corresponding to the samples taken by an ADC. Then once we apply the FFT to that vector, we get a new vector, vector K, which contains the frequency components of the signal. So how does the FFT algorithm go from S to K? Well, there are two steps to do this. First, S must be reordered, and secondly, we must then apply the main algorithm to that reordered vector. Now let's go over how step 1 works. We begin with vector S and label each element based on whether its index is even or odd. After that, we split the vector into two smaller vectors, one for the even indexed elements and one for the odd indexed elements. We then apply that same process again to each smaller vector. This repeating splitting continues until the groups have been reduced to just two elements each. To verify that the algorithm is correct, we must first create a software model of it in Python. The code shown here emulates the exact behavior of step 1. This software model will serve as our golden reference. Now let's move on to the second step. Before we can understand step 2, we must first explain the basic building block that makes the FFT possible. This building block is known as the butterfly operation. The butterfly operation takes in 3 complex numbers and produces 2 complex outputs. A simpler way to view it is in terms of real numbers, because every complex number contains a real part and an imaginary part. This operation can also be thought of as in taking in 6 real numbers and producing 4 real numbers. Although the butterfly operation can be fully defined by the 4 equations, it's more commonly represented in both industry and academic settings using the butterfly diagram shown below. Now that we have covered the butterfly operation, we can explain how the FFT is built. To implement an FFT, we repeatedly apply the butterfly operation. More specifically, these butterfly computations are organized into layers. If the input vector has length n, then the number of layers will always be log 2 of n. Within each layer, the butterfly operation is performed n over 2 times. The diagram to the right shows how the layer structure works. Each layer takes in a vector of complex numbers and produces a new vector of complex numbers. The output of one layer always feeds into the next layer, but the way that the values are connected changes from layer to layer. Also note that the vector x0 is simply the sample vector s after it has been reordered in step 1. The code shown below executes the FFT algorithm that produces each new vector from one layer to the next. This code is especially useful because it shows how the butterfly blocks can be processed sequentially, one at a time. It also serves as a golden reference for verifying that the hardware implementation is correct. Although it is technically possible to build one very large combinational circuit that computes the entire FFT all at once, that approach does not scale very well for larger FFTs because it requires too many hardware resources. By using a sequential design instead, we can support much larger FFT sizes, although the execution time increases with the number of butterfly operations. The animation below shows exactly how the code sequentially processes each butterfly operation. So the main objective here is to implement the function shown on the right. When the reordered input vector is passed into this function, it produces the FFT of that vector. Also note that some of the function calls have been replaced with their underlying operations so that the algorithm is fully defined here. Once we have the Verilog that correctly emulates this function, we can begin running an FFT on the FPGA. To fully implement the FFT, we must first reorder the input vector using the getFFT input function and then pass that reordered data into the FFT algorithm. In other words, to implement the complete FFT in hardware, we would need RTL that emulates those two function calls back to back. In the next video, I will show you how to create a Verilog file that implements only the FFT function itself. The function that reorders the original vector will be left as an exercise. However, in the video after that, when we use the microblaze and IP blocks, the full process will be implemented. Alright, that's all for now, and I'll see you next time.